Imagine this. We're on a camping trip, far from the city lights. The fire crackles, the air is crisp, and above us, the night sky stretches endlessly, filled with stars. It's a moment where you can't help but wonder about the universe. As we gaze upward, we spot the constellation Orion. Two stars stand out, the brilliant blue star, Rigel, and the radiant red star, Betelgeuse. You begin to wonder, why are these stars such different colors? The light a star emits can tell us a lot about its temperature, stage in life, and types of energy it releases. Today, we'll explore the concept of light and use that information to decode the stories of Rigel and Betelgeuse. Let's find out what these two stars are trying to tell us. To understand what Rigel and Betelgeuse's light can tell us, we first need to understand light itself. Light travels in waves. No, not the ocean kind. Light consists of waves of energy moving through space. But just like ocean waves, light waves can be described by a few key properties: wavelength, frequency, and energy. Wavelength is the distance between two peaks of a wave. Shorter wavelengths have peaks that are closer together, while longer wavelengths have peaks that are more spread out. This ties directly to frequency, or how many waves pass a given point per second. Shorter wavelengths, where the peaks are tightly packed, have higher frequencies, because more waves pass by per second. Longer wavelengths, with peaks spread farther apart, result in lower frequencies. Finally, there's energy, which depends on wavelength and frequency. Which type of wave do you think would have more energy? A wave with shorter wavelength and high frequency, or one with a longer wavelength and low frequency? Pause the video and make a prediction. Shorter wavelengths, which have higher frequency, carry more energy. Energy increases as wavelength decreases. Wavelength, frequency, and energy are what scientists use to organize light into the electromagnetic spectrum. The electromagnetic spectrum is like a map of all the different types of light arranged by their wavelengths. At one end of the spectrum are long wavelengths with low energy. At the other end of the spectrum are short wavelengths with high energy. In the middle of the spectrum is visible light. This narrow range is the only part of the spectrum we can naturally see with our eyes. Beside visible light on the spectrum are types of light we can't see, like infrared and ultraviolet. Astronomers use many parts of the electromagnetic spectrum to study the universe. You'll get a more in-depth look at this spectrum in your lesson materials, but today we'll focus on three types of light: infrared, visible, and ultraviolet. What can these different types of light tell us about the stars? Let's start with a very common type of light: visible light. Visible light is all around us. It's seen in the green of tree leaves, the blue of the sky, or the soft orange hues of our campfire. All the colors of the rainbow are in this part of the electromagnetic spectrum. At one end of visible light is red with the longest wavelength. At the other end is violet with the shortest wavelength. But when it comes to studying stars, visible light offers much more than just pretty colors. For example, the color of a star's light reveals its surface temperature. Blue and white stars give off light with short, high-energy wavelengths, while red stars give off light with long, low-energy wavelengths. Based on these energy levels, which do you think has a higher surface temperature, a blue star or a red star? Blue stars, like Rigel, are much hotter than red stars, such as Betelgeuse. Hotter stars emit more high-energy blue light because they have much higher surface temperatures. In their cores, nuclear reactions happen more quickly, so they burn through their fuel faster and release more energy. Cooler stars, like Betelgeuse, have lower surface temperatures, burn their fuel more slowly, and emit lower energy red light. But temperature isn't the only thing visible light can reveal. By analyzing properties like luminosity and brightness, astronomers can estimate a star's size, distance from the Earth, and the total amount of light it emits. We'll explore some of these aspects in more detail in the next lesson. For now, let's move on to see what infrared light can reveal about Rigel and Betelgeuse. We can't see infrared light with our eyes, but it's still very important. It lies just beyond the red end of the visible spectrum. The word infrared actually means below red, referring to its place on the electromagnetic spectrum. This type of light has longer wavelengths and lower energy than visible light. You encounter infrared light every day, even though you can't see it with your eyes. The warmth you feel from the sun on your skin, even on a chilly day, is caused by infrared radiation. But what can infrared light tell us about stars? Infrared light is especially helpful for studying cooler stars, their outer layers, and regions covered in gas and dust. Visible light gets blocked by dust, but infrared light can pass through dusty areas, showing us details of star formation and the materials surrounding stars that would otherwise be hidden. When astronomers observe Betelgeuse using infrared light, they see a cool, dusty shell of gas being shed from the star. What might this observation tell us about Betelgeuse's stage in life? The material it's shedding is a sign that Betelgeuse has entered the later stages of its life cycle, on a slow path towards its eventual fate, a supernova explosion. Compared to Betelgeuse, Rigel emits far less infrared light. That might seem surprising. After all, isn't Rigel hotter? While Rigel's blue color does indicate that it's much hotter, most of its energy is concentrated at shorter wavelengths, like visible and ultraviolet light. Infrared light, which we often associate with heat on Earth, is actually more strongly emitted by cooler stars like Betelgeuse. This is because cooler stars release a larger portion of their energy at longer wavelengths, including infrared. So infrared light is a powerful tool for studying cooler stars, uncovering dusty regions and revealing hidden details like Betelgeuse's outer layers. But how can we learn more about hotter stars that don't emit infrared light as strongly? Let's check out what ultraviolet light can reveal about stars. Ultraviolet, or UV light, is named based on its place in the electromagnetic spectrum. It lies just beyond the violet end of visible light. Ultraviolet light has shorter wavelengths and higher energy. It's the part of sunlight responsible for sunburns, and it's used in technologies like sterilizing equipment because of its ability to kill bacteria and viruses. When it comes to stars, ultraviolet light helps astronomers study the most energetic and dynamic aspects of stars. It is especially useful for detecting intense radiation, fast-moving particles, and powerful stellar winds, which are more challenging to observe at other wavelengths. By observing stars like Rigel and Betelgeuse in ultraviolet light, astronomers gain insight into their energy output and the forces at work in their outer layers. Which star would you expect to emit more ultraviolet radiation, Rigel or Betelgeuse? Hotter stars like Rigel emit a significant amount of ultraviolet light. That's why astronomers focus on studying Rigel in this part of the spectrum. UV observations of Rigel reveal highly active outer layers and powerful stellar winds. These winds are streams of charged particles propelled outward by the star's immense energy. They shape Rigel's surrounding environment, carrying gas and dust far into space. While Betelgeuse is cooler and emits much less ultraviolet light, UV observations still offer valuable insights. They can reveal activity in its outer layers, such as the turbulent motions of gas as it sheds material during the later stages of its life. As we've seen, each type of light, visible, infrared, and ultraviolet, reveals unique clues about stars. Visible light helped us learn that Rigel is a hotter blue star, while Betelgeuse is a cooler red star nearing the end of its life. Infrared light revealed the dusty material Betelgeuse is shedding, while ultraviolet light showed the powerful stellar winds and high-energy radiation from Rigel. By combining information from across the electromagnetic spectrum, astronomers uncover the fascinating stories that stars like Rigel and Betelgeuse have to share about their past, present, and future. Now it's your chance to find the stories hidden in the universe. See you next time!
Hey, hey.